Okay, so we pick up with these application pieces that we talked about earlier. I said we would spend a little bit more time on them, and we will. Arc length. If you remember, if you have a circle with a central angle of theta and radius r, we say that the arc length is this portion of the circumference, the outside of the circle, that the word is subtends. It stretches, I guess, from one side of the angle to the other side, and we want to know what that length is. And so we wrote down this formula. S is equal to r theta, and the key is that you have to be working in radians. Now in geometry you learned a different formula. The formula was this. S equals the measure of the angle divided by 360 times 2 pi r. And you may wonder, how are those related? First of all, I like to use the radians one because it's shorter, it's much smaller. But we can get this formula, we can get the radians formula from the degrees formula. I'll show you, it's really quite simple. What's 2 over 360? 1 over 180. So you have the measure of an angle times pi over 180 times r. You see, if I simply move the 2 pi up here and the m out there, that I can come up with that? I mean, this is the same. If you take the measure of an angle and multiply it by pi and divide it by 180, have you seen this process before? We just got done doing it, didn't we? This is how you convert from degrees to radians. So you have the angle measure in radians, which is theta, times your radius, r. And there it is. What? You want me to write m pi r over over 180. You want me to write like that? Okay. I don't think people look at this and see. I think when people look at this, they say, "Oh, that's the formula we just used, that we just practiced to convert from degrees to radians. Measure of an angle times pi over 180." No? Okay, sorry. I'm just, yeah, you're right. This bottom one is the same as that. I think this just kind of stands out. Question, Caitlin. This is the degrees formula. It's just rewritten. 2 over 360 is 1 over 180. I have the pi right here. I have the m right out front. I have the r there. And so all you need to do is just kind of, stretch it, so to speak, in a way that you can understand that this is your conversion from degrees to radians. So that's your theta value. That's your conversion value times your radius r. So this is a nice short formula. Very nice short formula. We can do the exact same thing with area. If you take the area of a sector, so a sector is like a pie-shaped part of the circle, and that we want to find the area. And the letter we use to describe for area of a sector is K. All right, it's just everybody wants to know why you choose certain variables. There's stories behind why they choose certain variables. None of them are interesting except for maybe one. So it's just K. Well, X is kind of interesting. No, Y is not. I know, I was trying to be funny. Okay, so here's the formula that you get. You get 1/2 times r squared times theta. 1/2 r squared theta. Now it's like, where does that come from? Again, you have to be working in radians. The reason why you have to be working in radians comes from your geometry formula that you learned 2 years ago. I know that you all remember that the sector area in geometry was the measure of the angle divided by 360 times pi r squared. Now I'm going to kind of do the same thing I did over here to show you that these two are related. If you see it, great. If you don't, you're never going to have to reproduce it. I'm going to take the m and move it out. I'm also going to factor out a 1/2. I'm going to write pi over 180. So all I did is I just pulled it apart. Everybody see the 360? 2 times 180 is the 360. I've got the m, I've got the pi, I've got the r squared. When you take the measure of an angle in degrees and multiply it by pi over 180, that converts it to radians. So that's how you get it. 1/2, 1/2, r squared, r squared. This is the measure of your angle in radians. So, some people were quite adamant. They said, Mr. Gens, I don't like the new formulas in radians. Yet you don't have to like them. You don't. If you'd like to use your degrees ones all the time, you go ahead and do that. I'm never going to use them. I think that they're bulkier. I don't like them. Yeah. Because there's some things in Algebra 2 that you have, or some things in Algebra 2 that require the knowledge of geometry. Other schools teach Algebra 2 before geometry. Give me one. Are you sure Austin does? First of all, some schools do. Well, I know that there's a couple, but my point is that some do, and that may be kind of a fad in mathematics, but it's just happened over the recent few years where people have started to do geometry after Algebra 2. Okay. Wait. And I apologize. I wish you did remember. I would say this: if you took Algebra 2 your sophomore year or your freshman year, and geometry your sophomore year, you'd be complaining right now about not remembering Algebra 2. So, no. But I am saying that every year people refer back to the geometry piece, and I've gotten asked this question actually by a lot of people in the district: should we move geometry to after Algebra 2? And all I can say is, well, what's the number one piece of content that's covered on the ACTs and the MCAs? They're like algebra. And I said, and you want to remove kids a year from that. You want to remove them a year from that. So I know people that are taking geometry after Algebra 2, those schools. I know some of them are reconsidering moving it back in. And some schools, what they call Algebra 2 isn't our Algebra 2. It's what we call our intermediate Algebra 1, what the 9th graders take. So back when the state mandated that we switch things up, a lot of things happened. Good point, though. I got an idea. How about we take 3 years of geometry and 3 years of algebra? Then we would for sure remember it all, wouldn't we? Yeah. But then you'd have to let go. Then you'd have to let go of some of your other courses. So, but okay. Find the length of an arc on a circle of radius 24 that subtends a central angle of 60 degrees. So we've got a circle. We've got a radius of 24. We've got a central angle of 60 degrees. And what are we trying to find in this problem? We're trying to find arc length. And arc length is your S value. What's our formula? S equals R theta. Do you know R? 24. Do you know theta? Very good. You see 60 degrees. Mark my words, 82 people in college trig. Not everybody will do this on the test. Some people will actually take the 60 and plug it in right away and take 24 times 60. And I understand why. You're like, well, that's my angle measure. But in order to use this formula, there's a prerequisite. You have to be working in radians. And you know that 60 degrees is the same as pi over 3. We did that conversion very quickly. 24 times pi over 3, what is 1/3 of 24? 8, so we get 8 pi. So make sure that if you're going to use that formula that you put it into radians. And then it becomes very user-friendly. Example 6, find the area of a sector of a circle with radius 12 and central angle of pi over 3. So I've got this sector, got a radius of 12, an angle of pi over 3, and I'm looking for, it says the area of that sector. What's my formula for the area of the sector? One half r squared theta. Do we know r? 12 squared is 144 times theta. Pi over 3, so we convert it to 60 degrees, right? No. That's what people like to do because they think they have to convert it. If it's already in radians, let it be. Just use the pi over 3. And away we go. What's 1/2 of 144? 72 times pi over 3. What's 1/3 of 72? 24 pi. Done. Those are your two formulas at work. On the test, if you'd like to write the answer in decimal form, I would accept decimal form as well. If you'd like to write in terms of pi, that's fine too. What's that? The quiz tomorrow or on Wednesday is only in converting degrees to radians or radians to degrees. That one skill. I want you guys to feel like you can do that, do it quickly, and do it well. Example 7, I say go through coterminal angles worksheet. I gave you guys that the other day. Cole, you just asked for one. We did our coterminal angles worksheet. We also did our unit circle worksheet, so we're caught up. So now we just have this last example, and we're done for the day. Okay? All right. Now that we've learned about radians, there's applications to the use of radians in the real world. For example, do you know how many rotations in 1 minute your disk drive on your computer makes? Lots, yeah. Around, 5,000, okay? Maybe 5,400. Your table saw is going to turn anywhere from, say, 3,200 rotations per minute all the way up to, say, 6,000 rotations per minute. Anybody use a Dremel tool? You ever seen those Dremels? It's like a little battery-operated tool. It spins on the end. Some people use it to actually file down their dog's toenails and stuff like that. Use all sorts of uses for it. I use them to remove spikes from people's, like when your spike gets ground into your shoe, you gotta take it out. I notch it and then take a screwdriver. Those rotate like 35,000 rotations per minute, okay? A lot of rotations. Well, they want to talk about rotational speed or angular speed, and we can measure that. And if you think about speed, if I ask, Bryn, what was your approximate speed as you were coming to school this morning? Don't say over 80 or cops will. 38 miles an hour. Safe driver. Somebody said 55 earlier. Maybe too fast. I don't know. I don't know how your roads were. Mine were actually okay. 38 miles per hour. So miles per hour. If we're talking about angular speed, we're not talking about miles per hour. We're talking about radians or degrees per, not necessarily hour, but often minutes or seconds. Okay? So that's omega equals theta divided by t, and the Greek letter for omega, that may be the one you're used to seeing. That's the capital letter omega. It looks like a W, and some people just write W instead. Okay, but so it says omega equals theta over t, and what theta is your angle, rotation, and radians. So we say radians. And t is time, and often we say it's in seconds. And that's how we figure it out. Linear speed, we talk about, just like when Bryn traveled to school this morning, she had a linear speed of 38 miles per hour. Okay, We aren't going to use speed. We're going to use really the term velocity. V we'll use for velocity because we can have direction. And that's going to be S over P. Do you recognize that variable S? Where did that come from? Yeah, our arc length. You remember that S is equal to r theta. We're going to have to use that to calculate S. And so S is what we call distance. We knew it as arc length, and we're going to divide that again by time. Now, if we put these two together, we come up with a relationship for another linear speed equation. So we kind of take these three equations up there, we can use them all to come up with a new one for linear speed, and that's velocity is actually equal to r times omega. And we can use that to our benefit later on. By the way, I tried to take notes. Anyway, here we go. Let's try it. Bicycle wheel that is 24 inches in diameter rotates 100 rotations per minute. So we got bicycle. All the way across is 24. It rotates 100 rotations per minute. I'm going to find the angular speed. And we're going to express it in seconds, okay? That's really the traditional way of doing it. You could leave it in minutes if it was all right with that. So we're going to find the angular speed and the linear speed both in seconds, okay? So I'll just write down my information, angular, and I'll write down linear. What is the formula for angular speed? Omega equals theta over t. Alright, so how much time has gone by? It says 100 rotations per minute. So per minute, how many seconds have gone by? 60 seconds. Now here's the tricky part for people to think about. What is one rotation in radians? 2 pi. So one rotation in radians is 2 pi. How many rotations has this made? 100 rotations. Okay, so over the course of 60 seconds, how many radians has this covered? 2 pi times 100. We take 2 pi, which is one rotation, and we multiply by the number of rotations, and that's our theta value. So we have 2 pi times 100 radians per 60 seconds. So we'll just simplify this. You should be able to express your answers in two ways. You should be able to write in terms of pi or as a decimal. We'll write the first one in terms of pi. We'll do the second one as a decimal just to give you a taste of each. So this ends up being 200 pi radians per 60 seconds. I can divide both by a factor of 10. So I get 20 pi radians per 6 seconds. 20 over 6 reduces to 10 pi over 3. 10 pi over 3 radians per second. Yep, that's thank you. Alright, so that's our answer, and it's in terms of pi. 10 pi over 3 radians per second. That's our angular speed. Okay? That's how many radians it's covering in every second. Now our linear speed, we have a formula. It says velocity is equal to s divided by t. So how much time has gone by? 60 seconds. S is our distance that we've covered, okay? It's our arc length. How do we find arc length? What do we do? We have to take r multiplied by theta. What is your radius? 12. So 12 was r times theta. Our theta value ended up being 200 pi. And we're working in inches. So I'll just multiply that on my calculator and see what I get as a decimal. I have 12 times 200 times pi, and I divide it by 60. I get 125.66 inches per second. I actually had a different option for that second problem. Did you see what we could have done instead? We could have done velocity equals r omega. You know what r is? What's r? 12. And you know what omega is because you just figured it out right here, right? You would come up with the same thing. So you can use either formula. We'll use the second formula here because I think it will probably work a little bit quicker, a little bit better. So paddle wheel has a radius of 0.3 meters. What's a paddle wheel? Last hour they really struggled with this. They didn't like paddle wheel. Paddle boat. Yeah, anybody seen a paddle boat before? Has anybody been on a paddle boat? Where have you been on a paddle boat? You own a paddle boat. Oh, okay. Like a foot paddle boat. You paddle with your feet. Like you spin it with your feet, right? You like a bicycle paddle boat. Okay, cool. Anybody been on one that's not a foot-operated paddle boat? I went to prom my sophomore year. Yeah, good for me. And on my sophomore year prom, we had prom on a paddle boat. It was really cool. Yeah, it was a great time. So, they head up and down the Mississippi. They're much more popular down south. But so we got this paddle boat wheel, and maybe it's from a boat, maybe it's part of a sawmill, who knows what. Okay, and the fact is that water is going by. And the question here is, if the paddle wheel has a radius of 0.3 meters and rotates 80 rotations per minute, find the speed of the current. So we're wondering, what's the current of the water going by? That's what we'd like to find out. Well, I'm going to use my secondary formula. Okay, velocity equals r times omega. What is your radius? 0.3. And omega is theta divided by t. How much time has gone by? 60 seconds. And theta is my angle that I've rotated. What is one rotation? 2 pi, and so I have 80 rotations, so it'll be 160 pi. What? Meters. So we've got it set up. So take 0.3 times 160 times pi. I divide that by 60. I get 2.51. That's it. Question? Yes. Any other questions? Good question. Going once, twice, thrice. All right. Sure. I'll be with you right away. This is your assignment. These problems, I think they said I had already signed 46 once. So if I already signed it once, then I don't have to do it again. But those are involving arc length and sector area, and then this one involves speed. Okay.